Myself Sanjeev Ghoshal, Assistant Professor, Hooghly Mohsin College, West Bengal. I'm a participant in RC in Disaster Management, UGC HRDC Aligarh. Today my topic of presentation is Study of Constant System and its Symmetry. A constant system is one of the most important topic if we want to do any meaningful quantization of a theory. In quantum field theory, there are various methods of quantization, namely the Lagrangian and the Hamiltonian approach. Both the methods have some advantages and some disadvantages as well. Because Lagrangian method, the Lagrangian is written in a covariant manner, but at the same time there may be some undetermined multipliers which is not true variable. Whereas in Hamiltonian approach, though all the true variables is there, but it is not Lorentz covariant. So we want some advanced method of quantizations which will take both the benefits of Lagrangian Hamiltonian approach, and these are the BRST and VFV formalism for the quantization. So our main emphasis is this type of quantization procedure for the field theoretical models. Now, description of constant dynamics. Now, constants in general, a relation between phase space variables. That means a relation between momentum and velocity, not velocity, coordinate. So, in order to extract out the constraint from the Lagrangian, we find the canonical momenta from the Lagrangian. And in the expression, if there is no velocity at the right hand side, then the momenta cannot be inverted in terms of velocity. So we will get actually a relation between phase space variable, which is termed as the constraint in the system. Then we can define the canonical Hamiltonian as in terms of pi qi dot minus L. Though the Hamiltonian is not unique, we can replace it by the effective Hamiltonian, which is given by He is equals to Hc plus um phi m. Now, classification of constants. Okay, physical consistency demands that the time derivative of the primary constants are to be 0 for all time, and necessary condition is that if we take the Poisson bracket of the constant with Hamiltonian, it must be 0. And the preservation may lead to two possibilities. It may give new constant or it may fix the velocities. So if it gives new constant, then that constants are called the secondary constant. So we have primary constant, which we get from the definition of the momenta, and from the conservation principle of time conservation criteria, we get the secondary constants. And then according to Dirac, we have two classifications of these constants. One is first class and another one is second class. If the Poisson bracket of a constraint with itself and the other constants is 0, it is called first class, and if it is non-zero, it is called second class constants. Dirac bracket and its importance. The Dirac bracket is a generalization of the Poisson bracket to treat second class constants. Now for second class constant, the Poisson bracket of phi 1, phi 2 is non-zero. So the right hand side is non-zero, but phi 1 and phi 2 are constant that must vanish on the physical state. So this is the example that illustrates that we need some generalization of the Poisson bracket which respects the system constants as well as it is consistent with the quantization procedure. Then according to Dirac, we can replace the Poisson bracket by the Dirac bracket in such a way that if we take any variables and take the bracket, Dirac bracket with the constant, it will give a 0 value, and that is an essential condition to set all the second class constants from the 0. Now, gauge invariance. Okay, symmetry plays a pivotal role in understanding the theoretical physics, and a gauge symmetric theory always has some advantage where the symmetry is lacking. So in terms of constraint, a gauge invariant theory is defined as a theory with first class constant, and a theory with second class constant means it is anomalous. Now, gauge symmetry can be restored in two different ways. One is to extend the phase space, the auxiliary space, which is known long past. Another way of restoration of gauge symmetry is available where the extension of phase space is not needed. Restoration of symmetry takes place in the usual phase space. Now, from the symmetry, if the Lagrangian is symmetric under some gauge invariance, then according to Noether's theorem, there must be some conserved quantity, and that quantity can be uh, termed as the conserved charge. So this charge can be interpreted as a generator of the symmetry transformation, because Q dot is 0. So Q, if it takes the Poisson bracket with Hamiltonian, where Hamiltonian is the actually Q is the generator of the symmetry transformation.